So, good afternoon. Hello, attention please. Yeah. Dear members of Vilnius University community and guests, it is a great pleasure to introduce William Daniel Phillips, who is a distinguished professor at the University of Maryland and fellow of the National Institute of Standards and Technology at NIST in the United States of America. Professor Phillips received his PhD at the Massachusetts Institute of Technology, known as MIT, and subsequently completed his postdoctoral research also at this institution before becoming member of National Institute of Science and Technology. Professor Phillips contributed significantly to the field of atomic and optical physics, as well more generally to the field of quantum optics. He received numerous awards, including 1997 Nobel Prize in Physics. Interestingly, Nobel Prize was announced just today, and today's winners are Alan Esper, John Clauser, and Anton Zollinger. And they got this prize for research which is closely related to research activities of Professor Phillips. This public lecture was supposed to be a part of 14th European Conference on Atoms, Molecules, and Photons, which took place this summer at the end of June in Vilnius, Lithuania. And but it appeared that Professor Phillips was not able to come to Vilnius because he was diagnosed with coronavirus just before this public lecture, just before this event, before this conference. But fortunately, Professor Phillips agreed to come to Vilnius, and finally this public lecture with some delay takes place. And this public lecture was organized, and the whole visit by Professor Phillips was organized by Vilnius University, Lithuanian Physical Society, with assistance of company Creativa. We are grateful to our sponsors, Vilnius University Foundation, Lithuanian laser company Light Conversion, European Journal of Physics D, and Gediminas Kuprevičius. As well, we are also grateful to our partners, Vilnius City Development Agency, Go Vilnius. Professor Phillips, it's very nice to have you here. We are looking forward for your public lecture.
Thank you very much. Thank you.
Thank you. Have a microphone, please.
Thanks very much. Now, first of all, I want to say that this portable microphone that I'm wearing keeps switching between green and red, and I'm not sure what that means. But if it stops working, you'll let me know and we'll fix it, right? Okay, great. Now, time, Einstein, and the coolest stuff in the universe. Well, as you've heard, I'm from NIST and the University of Maryland, the Joint Quantum Institute, which is a joint operation between them. At NIST, I'm part of the Laser Cooling and Trapping Group. Gretchen Campbell is the group leader, and Paulette, Trey Porto, Ian Spielman, who will arrive here in Vilnius tomorrow to work on things of common interest to us. Ida Tietzinger, Charles Clark, and Nicole Younger-Halpern are the other permanent members of the group, and it's a pleasure for me to work with them on a daily basis. Before we start, are there any children in the audience? I'm looking for children. Okay, I want to invite you, along with your parents, to come to the front, because it's a lot more exciting to be in the front, and it's only a little more dangerous. So if you'd like to come for the front, we've got a lot of seats here ready for you to be there. So you want to come? Sure, it's absolutely. So now I think you may have to let these children in to this row of seats. I think, great. Oh, this is wonderful. Absolutely fantastic. I'm so happy. I guess I should have said something about the people who are supporting us, the National Science Foundation, the Office of Naval Research, and the Institute for Robust Quantum Simulation. But here's the important thing. We're going to have fun this evening, okay? And so do be aware that there is going to be a lot of fun happening today. And the other thing is, as we go along, I want you to think of questions that you might ask, because at the end, we're going to have a question period, and everyone who asks a question will get a prize, okay? So it has to be a substantive question. Now, what I mean by a substantive question is any question other than, what is the prize? Okay? So, time, Einstein, and the coolest stuff in the universe. Oh dear. I now realize that my computer's been set up in the wrong mode so that I can't see what's coming next. So let's hope that I can do this. Okay, that still looks, okay, time, Einstein, and the coolest stuff in the universe. Well, you might ask, well, what does time have to do with Einstein? And the answer is that Time put Einstein on the cover of their magazine as the person of the century. And I think it was a really good choice because Einstein did all kinds of things. So this list of things that Einstein did really changed the way we think about the world, and in fact changed our technology. So for example, Brownian motion was the thing that convinced people that matter is made up of atoms and molecules. Now, can you imagine that only a little bit more than 100 years ago, not everyone was convinced in the 20th century that matter is made up of atoms and molecules? It was Einstein who really nailed that down. Stimulated emission, that's the thing that makes lasers work. Where would we be without lasers in optical communications today? But probably the thing that Einstein is most remembered for is his theory of special relativity. The theory that we often say is a theory of time and space that changes our very notion of what time and space are. Before Einstein, people thought that time and space were like an unchanging stage that the events of the universe took place on, like the stage I'm standing on. But what Einstein taught us was that the stage is part of the action. And special relativity, as well as general relativity, just changed that whole notion about time and space. One of the things that we often say about Einstein's theory is that time is relative. But Einstein came to that conclusion about the relativity of time by asking himself a question that I think people must have been asking themselves since the beginning of at least human time. What is time? And the answer that he gave may seem a little superficial. He said time is what a clock measures. But if time is what a clock measures, then what is a clock? Well, for me, a clock is something that ticks. The earliest clock is the rotating Earth. Now, ancient people did not know that the Earth was rotating, but they saw the sun rise and set every day, and in that way they could tick off days. When they became more sophisticated, they built sundials and they could tick off hours. There's a legend that Galileo was sitting in the cathedral in Pisa watching the chandelier swing back and forth instead of paying attention to the worship service. And what he discovered was, according to legend, was that the time it took for the pendulum to swing back and forth was independent of how far it was swinging. And he concluded that this would make a really good clock. And people like Christian Huygens made clocks using a pendulum as the ticker. And here's a picture of a grandfather's clock or a tall clock that uses the swinging pendulum. I'm wearing a quartz wristwatch. Inside this watch is a tuning fork-shaped quartz crystal, and the vibration of that quartz crystal is the ticker for this clock. All these clocks have different tickers. Some of these clocks are absolutely marvels of engineering. Some of them are famous, some of them are modern, some of them are historic. Here's one you may recognize, a wonderful modern clock that counts down to a really historic occasion. I was so pleased to be able to visit that clock in my visit here in Vilnius, which has been absolutely wonderful. But the thing that I want to emphasize is that every one of these clocks have tickers that are imperfect. The period of a pendulum, the ticking of a pendulum, is almost independent of how far it swings, but it is not at all independent of how long the pendulum is. And so if it shrinks or stretches, that's going to change the period of the pendulum. Every quartz watch is a little bit different from every other quartz watch, and it may keep a little bit different time depending on whether you wear it on your wrist or whether you leave it on the table beside your bed. Even the rotation of the Earth is not constant. It is slowed down by the friction of tides, the changing of ocean currents. This fact was brought home to me in a very dramatic way one day when I was visiting the U.S. National Naval Observatory. Now, naval observatories keep time. It's very important for naval navigation historically, and they had these wonderful clocks there. So I went to visit them to see some of these new clocks, and as we're walking along the hallway to the laboratory, I see a door, and on the door it's written, Director of Earth Rotation. Seems like a pretty responsible job. You wonder what happens if that person goes on vacation. The point is, somebody is keeping track of the variations in the rotation of the Earth for those people who still need to know about those kinds of things. So all of these clocks are imperfect. The best clocks are atomic clocks, where the atoms are the tickers. The intrinsic frequencies of an atom can be used as the ticker for an atomic clock. And one of the greatest things about these atomic clocks is that an atom of a particular kind, say Cesium-133, which is actually the atom that we use to define what we mean by 1 second in today's world. As far as we know, every Cesium-133 atom in the entire universe is identical to every other one. And so it's a really good thing to make a clock out of. And they're very little affected by the environment. For one thing, we put them in a vacuum and we shield them from magnetic fields, so they make really great clocks. Now you might ask, well, how good are these clocks? Well, for less than $100, you could buy a quartz watch like this, and it would be good to about 1 second in, well, let's see, what do I say it is? It's good to a part in a million, which is about 30 seconds in a year, okay? For $100. For $100,000, you can buy a clock that is good to a part in 10 to the 12. That's 30 seconds in a million years. Now you might say $100,000 for a clock, but think about this. You pay 1,000 times more money and you get 1,000,000 times better performance. I think that's a bargain. But you still might ask yourself, why does anybody need to know what time it is to that level of precision? Because after all, we don't need to know what time it is to be able to figure out when to go to lunch. But what I want to convince you of now is that you are very happy that somebody is keeping track of what time it is to that level of precision for things that do matter to you in your daily life. I found this article, this advertisement in an airline magazine. It says, if you're in our car and you get into trouble, don't worry because help is only 10,000 miles away. In other words, about 15,000 kilometers. And the distance they're talking about is the distance to the satellites of the satellite navigation system. How does that satellite navigation system work? It works by having atomic clocks in something on the order of 24 satellites that are constantly orbiting the Earth. And those atomic clocks are good to about a part in 10 to the 12, a part in a million. These clocks cost a whole lot more than $100,000, because when you put something in space, you have to space qualify it, and you know, it has all these things. But they are of a similar quality to the kind of thing you could buy for $100,000. How does this whole business work? Well, here is sort of a cartoon to show how this satellite navigation system works. Here is a satellite. It's got an atomic clock on board. Here's another satellite with an atomic clock on board. You synchronize those clocks. Here you are on the ground. You do not have an atomic clock, okay? But let's pretend for a moment that you do, just to see how this works. Imagine that you did have an atomic clock and all the clocks were synchronized, okay? Now, these clocks, the one that are in orbit, are broadcasting what time it is. So they broadcast that information, and the information goes to you on the ground at the speed of light. And when you receive a signal from one of these satellites, you see what time it was on the satellite when that signal left the satellite. In other words, the time is going to be earlier than your time, because it takes a certain amount of time for the time signal to get to your clock. Isn't it amazing how many times you use the word time when you're talking about time? And because you know what the speed of light is, you know how far away you are from the satellite. Now, the satellite is not only telling you what time it is, it's also telling you where it is. So you know now how far away you are from something that you know where it is. That means you know you're somewhere along this curve. And that's great, but not what we want. But of course, there's another satellite. And when you get the signal from the other satellite, then you know that you're at the intersection of these curves, because you know where that satellite is and you know how far away you are from that satellite. So you know what happened. So anyway, you get the idea, right? You know you're at the intersection of those surfaces. Now, if we lived in a two-dimensional universe, like the screen here, that would be all you would need, is two satellites. But we don't. We live in a three-dimensional universe, so you need three satellites. If you had an atomic clock, then you would only need three satellites, but you don't. So we need a fourth one, and that is sort of acts as your clock. So when your satellite navigation system, why this thing turns black, I have no idea. But when it can see four satellites, you know, sometimes when you turn it on, it says searching for satellites. When you've got four, you're ready to go. And this is the reason. And this, you know, has been amazing in the way it's changed our lives. Cars and taxis and delivery trucks operate using the satellite navigation system. I think it's gotten to the point that some people would not be able to find their way to the grocery store in their neighborhood if they didn't have their satellite navigation on. This is how much it has changed our lives. Now, you might ask, what do these atomic clocks look like? Well, in another magazine, I found this advertisement. It said, recently, the atomic clock in Braunschweig, Germany, was set back 1 full second. And our flight schedules have been adjusted accordingly. Yeah, right. The airline that made this advertisement doesn't exist anymore. And, you know, they got a little bit of it wrong. It's true that the atomic clock has to be adjusted from time to time, but it's done internationally, not just in Germany. And the reason is that what I told you about the rotation of the Earth. The fact that the Earth's rotation changes whenever it gets out of sync with the atomic time by more than 9/10 of a second, then they make a switch so that Earth rotation time and atomic time are the same. And that's what we call leap seconds. And that actually happens. I don't know, the last one was a few years ago. But that's not the point of this slide. The point of this slide is that the instrument in front of which these two dorks are standing looks nothing like an atomic clock. Here is a picture of what an atomic clock of a few years ago in fact looks like. There are cesium atoms running down the length of this clock. And the general idea, the sort of oversimplified version of it is, you shine microwaves on the cesium atoms at about the right frequency to cause the energy level of the cesium atom to change. The energy levels are the thing that determines the intrinsic frequencies. When the frequency is just right, then the cesium atom changes, and you can tell. And when the frequency isn't just right, the cesium atom doesn't change, and you can tell. And so you just tune the frequency until it's making the cesium atom change, and that means the frequency is just the frequency that you want, namely this number right here, because by international agreement, that's the frequency of the cesium atoms, and that defines what we mean by a second. The fact that that frequency is a certain number of gigahertz means that this number, 9 billion and some number of periods is what we agree is 1 second. And that's the oversimplified version of how an atomic clock works. The slightly less oversimplified version is that you've got a beam of cesium atoms. You have a can and you heat it up so the cesium melts and vaporizes, and the atoms come out here going more than 100 meters per second, and you shine the microwaves on them while they're zipping along. Now here's the problem. These clocks are amazingly good. The best of these clocks are good to about a part in 10 to the 14. That's almost unimaginably wonderful. 100 million, a part in 100 million. But at the National Institute of Standards and Technology, we are not satisfied with a part in 10 to the 14. We want to do better. And there's good reasons why we want to do better, both scientific and technological. But we can't because the atoms are going so fast. At more than 100 meters per second, it's really hard to measure these atoms. I mean, imagine what it would take to tell time with a clock that was going past you at the speed of sound and then crashing into the wall. Not so easy, right? But years, decades of engineering experience has made those clocks go to a part in 10 to the 14, but they've reached the limit. And what are the things that limit it? Well, just how much time you have to look at it. You don't have very much time to look at the atoms, and when you don't have much time to look at them, you can't make a good measurement. But there's more. The Doppler shift. Imagine you were on the seashore, and you're watching the waves come into the shore. You could time how many waves come in per second or per minute or whatever. This would be the frequency of the waves hitting the shore. Now let's say you got into a boat and went into the waves. You would see the waves hitting the front of your boat more frequently, at a higher frequency. That's the Doppler shift. It says if you're moving into a source of waves, then you're going to see the frequency be higher. You can experience this if you stand by the road and listen to cars go by. You might hear something like, as the car goes by. So when the car is going toward you, everything is shifted to high frequencies, and when it goes away from you, it's shifted to lower frequencies. Well, the same thing happens with atoms. And these things are moving around really fast, and this messes things up. And finally, remember about the relativity of time. Einstein taught us that time was different for different observers. If you're moving, your time is different from people who aren't moving relative to you. And that's a big problem with these atoms. So for all these reasons, what we needed to do was to make the atoms go more slowly, because we want to improve the performance of the clocks. And this is really a central message of this talk, is that it's easier to measure the atoms and you get better results if the atoms are moving more slowly. And that means cooling them down, because the difference between hot and cold is the difference between fast and slow. A hot gas, like the air in this room, and it's feeling kind of hot to me, so I think I'm going to take my jacket off. The molecules and atoms in the air in this room are moving at about the speed of sound. If we could cool down the air, then it would mean that the atoms and molecules would be moving more slowly. In fact, temperature is just a measure of what we call the kinetic energy, the energy of motion of the atoms. The higher the kinetic energy, the hotter the temperature. So what we want to do is to cool the atoms down. Now, in order to give you an idea of what's involved in getting the atoms cold enough to make a difference, and thanks to the physics department here at the university, I brought along some really cold stuff. Inside here, I have liquid nitrogen. Now, nitrogen is the major constituent of the air. That means this is like liquid air. Unless you've been in a low-temperature physics laboratory, this is probably the coldest stuff you have ever seen. This is so cold that compared to it, the floor on which I'm standing is burning hot. Imagine what would happen if you took a bucket of cold water and spilled it onto a red-hot stove. You know what would happen. The water would boil. And when I pour this liquid nitrogen onto the floor, which is like a red-hot stove, it boils. That liquid nitrogen, you see, it's gone. It's boiled away because the floor is so hot compared to the liquid nitrogen that it just made it boil. So you might think that if we have something as cold as this, probably the coldest stuff you've ever seen, then it might be a good idea to use this to cool down a gas to make the atoms and molecules move more slowly. So that's exactly what we're going to do now. Now I've got a bucket here. I don't know, can you see this bucket? Yes, I think you can. I've got a bucket here which we filled up with liquid nitrogen before the lecture. So I'm just going to put a little bit more in because a little bit of it has boiled off. And now what I'm going to do is I'm going to take a balloon, a yellow balloon, one of the colors of the Lithuanian flag, and I'm going to blow it up. So now this thing is full of hot gas, okay? The atoms and molecules are moving around really fast, around the speed of sound, 300 meters per second, really fast. And I'm going to stuff this thing into this full bucket of liquid nitrogen to cool down the gas molecules. Oh, I can see a lot of liquid nitrogen spilling out. So that's always fun. Okay, there we go. Okay, great. So that's cooling down and making the atoms and molecules move more slowly. Now let's see what else we can do. Okay, over here I have what is called a Dewar flask. It's just a thermos bottle. It's a fancy name for a thermos bottle, okay? It's been sitting out in the air all day. That means that it's at room temperature, which compared to the liquid nitrogen is burning hot, right? So imagine what would happen if you took a metal bucket and heated it up in a fire until it was glowing red. That's what this is compared to the liquid nitrogen. And then you poured cold water into the red-hot bucket. What would happen? Well, it would cause the water to boil, and that's what's happening here. Don't try this at home. Okay, so while that's cooling down the bucket, let's cool down some more gas. So what do we have next? Green. Okay, I think that's big enough now. I think that we might have to push it in, but you know, let's see what happens. Okay, great. Just put that in there. Okay, wonderful. Now let's go back to our Dewar over here. Well, some of the liquid nitrogen has boiled off, as you can well imagine. So let's top it up. Oh, gee, that's empty, so we're going to have to get this baby refilled. So let's just top it up a little more, and we'll do this one too, even though it's not quite empty. Okay, so now I've got a full bucket. So imagine what would happen if you took something like this flour, been sitting out all day at room temperature. Compared to the liquid nitrogen, this flour is red hot. In fact, it's even red. So imagine you took something like a metal rod, like a fireplace poker, and you put it in the fire until it was glowing red. And then you took it out of the fire and plunged it into a bucket of cold water. What would happen? It would make the water boil. And that's what's happening here. And I look in here and I can see the water is boiling away. Not the water, the liquid nitrogen is boiling away, cooling the flour down to the temperature of the liquid nitrogen. So, while we're waiting for it to cool down, let's put it in some more hot gas. Okay, so now we've got yellow, green, and red in here. Are you remembering how many balloons are going in and what their colors are? Good, because it's important. Okay, great. Now, let's go back to the flour. So I look in here, the boiling has stopped. This flour has cooled down to the temperature of liquid nitrogen. This flour is so cold that when I pull it out, I can crush it like it was made out of glass. This stuff is really, really cold. And, you know, if you've got something that cold, then why not use it to cool down your gas? So the atoms and molecules will move more slowly, because, of course, that's the whole idea. We want to make the atoms and molecules move more slowly, so we're cooling them down with liquid nitrogen, the coldest stuff that most of you have ever seen. Okay, great. Now let's see what else we can do. Okay, now I'm sure that, so how are we doing with the pitcher tour? Do we have some liquid nitrogen ready to go there? Let's just go with it as it is, and then we'll fill it up some more later. Okay, great. Thank you very much. Okay, now, when you were young, and some of you are still young, I'm sure that when you started to learn how to do things in the kitchen, that your parents told you that you must never, ever put a closed container of liquid into the oven. Well, here we have a liquid, and here we have a container, which I'm able to close. And I'm going to pour the liquid nitrogen into this container. Very carefully. That's enough. And I'm going to take it over here. And this whole room, compared to this liquid nitrogen, this whole room is an oven. So let's see what happens. Okay, great. Now, let's see what else we can do. Oh, okay, great. Here I have a rubber ball. Nice bouncy rubber ball. Let's see what happens when it goes into the liquid nitrogen. Okay, and while we're waiting for that to cool down, let's cool down some more gas. What? I mean, sure, it's getting a little crowded in there, but if I push the balloons in, I'm sure there's plenty of room. Okay, great. And just for good measure, let's cool down some more stuff. Okay, great. Okay, wonderful. Now, let's see what else we can do to give you an understanding of just how cold this stuff is. Here is a rubber band. It's a nice, stretchy rubber band. What I'm going to do is to put the rubber band into the liquid nitrogen. Now, it's making the liquid nitrogen boil because that's what happens when you put anything warm into the liquid nitrogen. It's so much hotter than the liquid nitrogen that it makes it boil. But it doesn't take too long before the boiling stops. That means the rubber band is now down to the temperature of the liquid nitrogen. Let me come out here so you can see this a little better. Okay, when I take this thing out, it is frozen so hard that I can snap it as if it were a dry twig. But all I have to do is warm it up in my hands, and it's a nice stretchy rubber band again. This stuff is really, really cold. And if you got something that cold, well, let's see what happened to the rubber ball. Remember how nice and bouncy it was before? It breaks like it was made out of porcelain. This stuff is really, really cold. And when you have something that cold, well, it seems perfectly reasonable that you should use it to cool down a gas, which is what we were doing with these balloons. Now, just how cold is it? Well, in order to understand how cold it is, we have to talk about the way physicists like to measure temperatures. Now, around here, in the wintertime, it often gets below zero, right? But physicists don't like this below zero stuff because it's just annoying. So we have a different temperature scale called the Kelvin scale, where the lowest temperature possible, imaginable, is what we call zero. It's called absolute zero, okay? Measuring up from absolute zero in Celsius degrees, room temperature is about 300, okay? Ice melts at about 273. Dry ice is about 195. The coldest temperature ever measured on the surface of the Earth, someplace in Antarctica during the winter, was 185, okay? 185 degrees, coldest temperature ever measured on Earth. This stuff, which boils when you pour it out on the ground, that's probably the coldest thing you've ever seen. This stuff is 77 degrees above absolute zero. 77 degrees. That's incredibly cold. 77 degrees above absolute zero. And so it seemed like a good idea to use it to cool down our balloons. Now, I get the impression that some of the more observant of you may have thought that the number of balloons that went in, that the volume of the balloons, whoa! Fantastic! Ah! Your parents were right. You should never, ever put a closed container of liquid into the oven, because this is what happens. So now, maybe right now I should just say something about safety, because I can imagine some of you are thinking, yeah, I want to do that. I hope that's true of you kids. But what I want to tell you is the way you have this kind of fun is you study science now, and you grow up to be a scientist, and then you get to play with toys like this all the time. That's what scientists do, is play with really cool toys, and really expensive toys too. I mean, it's fantastic. And you see, I've been working with liquid nitrogen for over 50 years, and had regular safety training, so I know how to do things so that I'm safe and so that you're safe. And so that's what you do. When you grow up and study these things, you learn how to do all this stuff safely and just have so much fun. What were we talking about? Oh yeah, the fact that there's too many balloons in here. The volume of the balloons is too big. How many? 7. Okay, let's go here. You see, how could we put that many balloons in here? And the answer is that these balloons are as flat as pancakes. They are like Frisbees. Okay, so is that the right number now? Yellow balloons and green balloons, or at least one green balloon, and red balloons. Now, what I want to ask you is, what about purple balloons? What about pink balloons? What about silver balloons? How about orange? How about white? What about black? So before we started, I put all those extra balloons in there. And the reason that they fit is that every one of those balloons became as flat as a pancake. Why? Because if you take a gas, any gas, and put it into a container, and then you cool the container down, the gas is going to condense into a liquid or a solid, or it's going to stick to the walls of the container, and you will not have a gas anymore. And we needed to have a gas because when we do this atomic clock business, we have to have the atoms floating freely in space. We can't have them stuck onto other atoms. We can't have them stuck onto the inside of a container. They've got to be floating freely in space. So this isn't going to work. So the question is, how are we going to get atoms cold without touching them with a cold surface? And the answer has been staring at us from the heavens for centuries, because since the time of Kepler, people have known that the tails of comets point away from the sun. So if you have a comet coming in from somewhere out here in the Oort cloud, as it comes in, gets close to the sun heats up the dust and gas that are in the comet and pushes on the dust to make it head away from the sun. And so as the comet comes in, the tail streams behind it, and as the comet goes around the sun and goes back in front, the tail streams in front of the comet. And that's because of the pressure of the light pushing on the dust that is in the comet. What we're going to do is we're going to push on atoms with that same force and make them slow down, and that's going to make them cold. Now, first of all, we got to admit that the whole idea of laser cooling is absolutely ridiculous. We all know that if you shine light on something, it gets warm. And I'm telling you that I know how to shine light on stuff so it gets cold. So here's the deal. First, we have to talk about resonance. If I've got a gas, like the air in this room, and I shine light through it, it goes right through because the air is transparent. That's why we can see each other, is because the air is transparent. However, if the light has just the right color for just the right gas, then the gas will absorb the light. It won't get through. Now, it has to be just right. So, for example, let's say you had a gas of sodium atoms. Now, you've seen these yellow street lamps. What's inside those yellow street lamps is a gas of sodium. And if you put the yellow light, just the right color of yellow light that comes out of those lamps, into the lamp, it would be absorbed by the gas that's there. But you'd have to get the color just right. Light is just like radio waves and microwaves. It's electric and magnetic field shaking around at a very high frequency. The frequency of light is about 10 to the 15 cycles per second. What's that? 1,000 million cycles per second, whereas radio waves might be 100 million cycles per second. So it's really fast. If you don't get the frequency right to within like 10 to the 7, that's a part in 100 million. You've got to get the frequency right to a part in 100 million, or the atoms won't absorb the light. You would never be able to tell the difference between two colors that were a part in 100 million apart. If I showed you two different colors of light, you would never be able to tell the difference. But the atoms can tell, because the atoms are so incredibly sensitive to the color. So that's one thing to understand, is the atoms are extremely sensitive to what the color is. The other is the Doppler shift. Remember we talked about the Doppler shift, how the frequency of water waves would change if you were moving into it. Same is true of light. So if an atom were to move into a light field, say coming from a laser, then it would look like the frequency of the light was a little bit higher, which is to say its color is a little bit bluer. You would never be able to tell the difference, but the atoms can tell because they're so sensitive. So that's the idea. So here's a cartoon that shows how it works. Here comes a laser beam. Now this laser beam has been tuned. An atom moving this way is going to see the laser beam coming from that direction as being the right color. It absorbs it and slows down. And an atom going this way will see the laser beam coming from that direction as being the right color. And no matter which way the atom goes, it's beat back by the laser beam that opposes its motion. And that's the whole idea of laser cooling, that the atoms that are moving always see the laser that opposes their motion as being the one that they want to absorb light from, and so the light slows them down. And it works in 3 dimensions. You can bring in laser beams from top and bottom and backwards and forwards, and we call this optical molasses. Imagine you were in a swimming pool full of molasses, and you tried to move. No matter which way you go, it's going to feel like there's a force preventing you from moving, and the atoms feel the same way, and so they slow down. The idea behind this was due to these 4 people in 1975. Let's see if I can, whoops. Each one of those people got a Nobel Prize for something else. Which gives you some idea of how smart these people were, that they invented something as important as laser cooling, and they didn't even get the Nobel Prize for that. They got it for something else. The Nobel Prize for laser cooling went to Steve Chu and Claude Cohn-Tanuji and that guy with somewhat darker hair and beard. We and colleagues in groups all over the world have contributed to this understanding of laser cooling and related subjects, and people all over the world, including right here in Vilnius, are doing work involving cold atomic gases. So this theory group of Gediminas, who gave the very kind introduction at the beginning, doing amazing work, one of the pioneering work in what are called synthetic fields, and I wish I had time to tell you about it, but I don't. But coming back to laser cooling, here is a picture of taken in our laboratory, looking into a vacuum chamber where we have sodium atoms and laser beams coming in from all directions, and this little cloud of atoms, about 1 centimeter across, with about 100 million atoms, is supposed to be able to get down to a temperature of 240 microdegrees, 240 millionths of a degree above absolute zero. Now think about that. This stuff, which is the coldest stuff you've ever seen unless you've been in a low temperature physics laboratory, this stuff is 77 degrees above absolute zero, the coldest stuff you've ever seen. We're talking about getting a gas of atoms down to 240 millionths of a degree. That's something like 300 million times colder than this stuff. 300 million times colder than this stuff. That sounds like a pretty good idea, right? So how do you measure the temperature of something that cold? And the answer is, you see how fast the atoms are going. So you start with the atoms in this optical molasses, and the laser beams are making the atoms slow down and keeping them from moving very far. And then you turn the laser beams off, and then all of a sudden the atoms are exploding with whatever velocities they have, which is supposed to be on the order of 30 centimeters per second. So instead of 100 or a couple hundred meters per second, it's supposed to be 30 centimeters per second, okay? So Steve Chu and his colleagues did that, and they found, amazingly, that the temperature was 240 microkelvin, just what the theory said was the lowest temperature you could get, which was fantastic. We repeated those experiments a little bit later and got the same answer because we did exactly the same thing. And other people did too, and they got the same thing for different atoms. There's a different number expected, but they got the right answer. And then we started to do more experiments, which is what you do because you just fool around because it's fun. And we found it wasn't working the way it was supposed to. And so we decided we'd better measure the temperature a whole lot better. And we did that, and to our surprise, we found out that the temperature was, in fact, 6 times lower than the lowest possible temperature. Now, one of the most exciting things that can happen to a scientist is you prove that what everybody thought was right is, in fact, wrong. I mean, what could be more fun than that, to show that everybody's wrong? And that's what we're constantly trying to do because we're trying to learn something new. So when we saw this, you know, we felt like these guys who have seen something that is a whole lot colder than is allowed for the circumstances that they're in. And as a result of that, there were a lot of discussions about how to solve this problem because other people confirmed the experiments, so what was happening was we needed a new theory. And pretty soon, people came up with a new theory, and I wish I had time to tell you about it because it's so cool. But based on that new theory, which came from Jean Dalibard and Claude Cohen-Tanucci, we then went back to the lab, used that information to make things work better, and it wasn't very long before we had a gas of cesium atoms, the thing we use to keep time, at a temperature of 700 nanokelvin, which is about 200 times colder than we expected. So we started with 6 times colder than we expected. We went to 200 times colder than what we expected. This is 100 million times colder than liquid nitrogen. It's 4 million times colder than the temperature of outer space. If you go to outer space, far away from any stars or planets, the whole universe is filled with radiation that's left over from the Big Bang 14 billion years ago. And the temperature of that radiation is a little bit below 3 degrees above absolute zero. So this is essentially the coldest natural temperature in the universe. We are 4 million times colder than the coldest natural temperature in the universe. So when I say this is the coolest stuff in the universe, I'm not kidding. It really is incredibly cold. And the thermal velocity of these atoms is less than a centimeter per second. Remember, we started off with more than 100 meters per second, and now we're down to less than a centimeter per second. And to make a clock out of this, we have a whole different idea. This is Don Meekhoff and Steve Jeffords, and what they do is they cool cesium atoms down here. They launch them up inside this vacuum tube to a height of about 1 meter. They fall back down after about a second. And because of that longer time, instead of thousandths of a second, they have a whole second. They can make clocks that are now good to a few parts in 10 to the 16. And that idea of shooting them up and falling back down is sort of like this atomic fountain, or this water fountain, so we call it an atomic fountain. And these are the best primary standards, meaning using cesium, that has ever been made. So they're accurate to a little bit better than a second in 100 million years, and that's wonderful, a whole second. But what if you want to keep these things for even longer? What if you want to put them in some kind of a bottle? What kind of a container would you be able to put them in? Let's imagine that this bowl is the kind of container that you want to hold your atoms in. And let's imagine that this ping pong ball is the atom. if this container is hot, which it's going to be, compared, because the atoms are the coldest thing there ever has been. So if this container is hot, it means that the atoms and molecules in the container are jiggling around really fast. So if you tried to put a cold atom into it, those atoms and molecules would bounce this, the atom around, and you would lose it. Now, maybe I can, without coming down, I can get another one. But if the container were cold, which we don't know how to make a container that cold, the atoms would just stick. So it doesn't matter. You cannot use a container like this. You have to use a container that is not made out of any material. Let's do the let's do the video right now. So, what are we going to do? Well, it turns out that our atoms are like little tiny magnets. We're going to switch over to the video camera. Now, do you remember the first time you held two magnets in your hand? And you turned them the right way and you found out that they were pushing against each other without touching? Wasn't that an amazing feeling? I'm still amazed by that. Well, what we're going to do is we're going to show you how that works as soon as we get switched over. Okay, now we need to have the camera on here. Okay, so what I've got is a couple of magnets. And, right, okay, so you see that magnet? I can push on that magnet with another magnet without touching it. And that's what we're going to do to our atoms. We're going to push on the atoms, which are magnetic. We're going to push on those atoms in such a way as to suspend them in space without touching them. That way we can keep them cold and keep them around for a long time. Now let's go over here. Now, if you had enough magnets when you were a kid, and if you're still a kid and you don't have enough magnets, you have to demand that your parents give you some more magnets. You might have tried to see if you could make one of the magnets float above the other magnets, and it never works. But when you were young and playing with toys, you may have also learned that when you spin a top, it doesn't fall over. Well, it turns out that our magnets, our atoms, are like tiny spinning magnets. They're like a top. And the reason why you couldn't make your magnet float was because if you suspended it above your other magnets and let go of it, it would flip over and be attracted to the other magnets instead of being pushed up. But if you could spin that magnet, which I can right here, and raise this to the right place, then, if I'm lucky, I can make it float. Whoops. Well, okay, I can do better. And besides, you shouldn't applaud, because any two-bit magician can levitate a woman and then pass a ring around her, carefully missing the wires that are holding her up. But I'm going to do something that you don't see a magician do. So let's make this thing float again. See, the reason we had trouble was that the room got a little bit warmer because all of you are so hot. Each one of you is putting out about 100 watts of heat, and so we have to take off a little bit of weight from this spinning magnet to make up for the fact that when the magnet gets hotter, that it's weaker. And of course, every time I touch it, it makes the magnet hotter. So we'll hope that we can make this work, and so that it'll really stay suspended. Oh, you people are just so hot. I just can't. Okay, let me just try one more time to see if I can. See, we also made a video of a successful run of this, which we can show if we fail to do it live, but I think I can make it work. There we go. Now, you see, nothing holding it up, but that's just like what a magician does. You don't ever see a magician do this. This is complete, there's nothing holding this thing up. This is the real thing. And that's how we trap our atoms and hold them in place in a vacuum so that we can keep them around for a long time. Well, let's go back to the PowerPoint now. Okay, so that was the sort of toy version. Are we back on? No, we have to wait a few seconds because it takes a little time to turn over. Okay, are we back now? I think we're back. Okay, now, that was the toy version. Here's the real thing. This is a cloud of cesium atoms released into a magnetic trap, and the atoms are bouncing around because we had them a little bit off center, just like you saw the spinning top bouncing around a little bit. And as time goes on, the cesium atoms disappear because the vacuum is not perfect. Well, over time, we got better at making better vacuums, and now we can keep those things for not just a few seconds, but for a whole minute. And when we can keep atoms that long, we can make incredible clocks out of them. And there are experiments that are being done in our labs in Boulder, Colorado. Anna Maria Ray doing the theory and Junyi doing the experiments, trapping atoms in arrays of laser fields. Dave Wineland trapping charged atoms in an ion trap. These clocks, compared to even the amazing fountain clocks that are better than a second in 100 million years, these clocks are good in the case of the optical traps to 2 times 10 to the minus 18. And for the ion traps, 9 times 10 to the minus 19. And these people are dreaming to go to 10 to the minus 21. This is less than a second in the age of the universe, less than 1 second in 14 billion years. And this huge improvement got us to a second in 100 million years, and now, after a few more years of work, it's down to a second in the age of the universe. At the United States National Bureau of Standards, National Institute of Standards and Technology, an agency of the United States government, this is what we call close enough for government work. Well, we've been on an amazing odyssey of searching for lower and lower temperatures. This thermometer, it's a logarithmic thermometer. What that means is every tick mark on here changes the temperature by a factor of 10. The highest temperature, not the highest temperature there is, but pretty hot, the surface of the sun, about 6,000 degrees. Room temperature, 300 degrees, is just a little bit colder than the surface of the sun on this thermometer. Liquid nitrogen, this stuff that's the coldest stuff you've ever seen, 77 degrees. Outer space, just a little bit colder at 3 degrees. The first experiments that said that the temperature of optical molasses was 240 microkelvin, colder compared to the temperature of outer space than outer space is compared to the temperature of the sun. That's how cold we were getting things, but in fact, it was even colder. And so the first Sub-Doppler, well, not the first, but finally Sub-Doppler temperatures to 700 nanokelvin. I wish I'd had time to tell you about Bose-Einstein condensation. We can get the temperatures even lower, do something that Einstein only dreamed about back in the 1920s. 50 nanokelvin for the first of those experiments. But today, we get down to half of a nanokelvin, 500 picokelvin in the laboratory. And in space, people are doing even better. Simulating the microgravity of space by dropping an experiment in a tower, they've gotten down to 38 picokelvin. And with these atoms, we're doing all kinds of amazing things, like the things that are going on in theoretical studies here in Vilnius, studying the fundamental nature of quantum materials. We're going to make better clocks, and we're going to redefine what we mean by a second. We are looking forward to doing tests of Einstein's theories of special and general relativity better than has ever been possible before, to see whether we can find some variation in the way these most successful theories have have been working so far. Quantum computers. I wish I had time to tell you about quantum computers. New ways of doing computations that are more different from today's high-speed digital computers than those computers are from the ancient abacus. That's how big of a change in computing we're looking forward to, that we're just starting to do, and some of those things are being done with cold atoms. And maybe the most exciting thing that we're looking forward to is right here, the things we haven't yet done. And what I'm hoping is that some of the young people in this audience will join a research team like the one that I'm part of at NIST, where people from all over the world have come together to try to understand more and more about the secrets of the universe. And so we've come to the end of the talk, but you know, it's never the end because there's always something new to learn. Thanks very much. Thank you. Now, before we do the questions, which I'm really looking forward to, and of course, remember, there are prizes for everybody who asks questions. I want to thank all the people here in the university who have done so much to make this talk work. As you can see, it was pretty complicated. And without the help of all of these people, it would never have happened. So it's been wonderful. So thank you so much. Thank you.
So thank you very much, Professor Phillips, for here. Thank you very much, Professor Phillips, for this nice illuminating talks. Now, please, questions.
And remember, everyone gets prizes. Right. So, right. Okay. So. I mean, this is wonderful.
So I would like to ask about the lowest temperature.
Ah, yeah.
And how you measure the lowest temperature. Because in my understanding, if you measure, you have somehow to influence the atom. And this means that you heat the atom.
So
and
it's true.
Your measurement of the temperature should be like a limit.
Absolutely.
So could you
You're absolutely right. In
this?
fact, most of the ways we have of measuring the temperature destroy the atoms. So here's what we do. We have a procedure. We measure the temperature of the atoms, and they're destroyed. They're heated up, as you say. And we do it again in exactly the same way, and we measure it and get the same answer, but the atoms are destroyed. And then finally, when we're confident that if we use this procedure, the atoms are going to end up being cold, then we don't measure the temperature and we do something interesting with the atoms. And that's how we get to use these incredibly cold temperatures. Now, how do we measure it? Well, one of the ways is seeing how fast the atoms go. The lower the temperature is, the harder it is to measure, as you might imagine. And so we have to get kind of creative with ways of measuring the temperature when it gets really low, when it gets below a nanokelvin. But we have a number of tricks. But that's the general idea. So now, yes, oh, absolutely. Let's get questions over here.
What happens if you put fire in that cold bucket?
What happens if I put fire in the cold bucket? Does anybody have a match on them? Nobody smokes anymore, right? So nobody has a match. If we had a match, well, okay, that's sort of a fake match, right? I'm not sure whether I can drop this into there. Well, but the trouble is, no, I mean, I know you don't care about it. You're perfectly happy to sacrifice your lighter for science. The trouble is that the way this lighter works is that I have to hold it down, if I'm remembering correctly. And so if I dropped it in, I'd have to let go of it and it would go out. So I can't quite do the experiment that you're asking for, but I can tell you what I guess is going to happen. Oh, that's a very good idea. Oh, and these are matches. Okay. Wonderful. Okay, we'll give you this back. Oh, fantastic. So I'm going to bring this bucket over to you. And we're going to see what happens. See, this is the cool thing about science. The way you answer questions is you do the experiment and find out. Nature is the final answer. Okay, so here's your bucket of liquid nitrogen. You might want to stand up on your seat so you can see better. Okay, Great. Now what I'm going to do is I'm going to light one of these matches and just drop it into the liquid nitrogen. So let's see what happens. Okay, let's get it burning nicely. Okay, you got it? Now, just because I'm interested, I'm going to do something a little different now. I'm just going to slowly lower it in here without actually dropping it. And let's see what happens. It went out well before it touched the liquid. Now, what do you guess happened? Why, let's do it again. It's too bad the rest of you can't see this. This is fantastic.
There is no oxygen there.
There you go. You need oxygen for the flame to continue, but when you put it in here, it's just nitrogen. Yeah. And nitrogen doesn't support combustion, or life, for that matter. So if you were in a small closet and it was filled with nitrogen, then you'd suffocate. But you would never do that. So you had a question, yes?
Yes. What things do you use to do such a thing?
What things do we use to say, make liquid nitrogen?
Yes.
Ah, now there is a question. You use ordinary refrigerators, except refrigerators that work a lot better than the one in your kitchen, okay? So nitrogen is free because most of the air is nitrogen. So what you do is you make a refrigerator that can get colder than nitrogen. Well, how do you do that? You get some kind of a gas that will condense at a temperature lower than the temperature of liquid nitrogen. And this is the way a refrigerator works. You take that gas, you take that gas and you compress it, okay? Now compressing it heats it up. So now you got a hot gas, and you take the heat away by just sending the heat off into the air. Then you expand it, and that makes it cold. And you keep doing that until you've taken enough heat out of whatever you're working with that nitrogen will start to condense onto it. And that's how you make liquid nitrogen. It's a little bit more complicated than that because you got to make sure that it's pure nitrogen, that it doesn't have oxygen in it, that it doesn't have argon in it, that it doesn't have CO2 in it. But you know, people have figured out ways of doing that. So, so that's how we make liquid nitrogen. I mean, I don't do it. It's an industrial product. We buy it in tanker trucks. People deliver liquid nitrogen in huge tanker trucks, like the kind of thing they deliver oil or gasoline to a gasoline station. And it's just amazing how cheap it is. The price of liquid nitrogen is a lot less than the price of gasoline. It's even less than the price of water. If you buy water, it's a few cents a liter. That's how much liquid nitrogen costs because it's made in industrial quantities and it's free. You don't have to go mining for it. It's just in the air. And it's wonderful.
I don't know if this hears. Does it work?
Yeah, yeah.
Okay,
Yes.
so is it okay if I ask several questions? Because I have a few.
I'll have to ask my colleagues.
Of course.
Yeah. Okay, so first one's gonna be a pretty simple one. How many times do you think you said the words time and cool or something related to cold? I have roughly the amount you've said. So
Yeah, I don't know. I'm guessing a couple hundred.
no, actually, time was about 19 to 20,
Really?
and
Oh,
cold was
that's all?
about 38.
Really, that's all. I would have thought it was more. Okay.
Yeah.
Felt like more.
Okay, now I have a few more normal questions. So the first one is, do you think in the future, or how much time do you think it'll take us
How
to
much
create?
time?
Yes. How much time do you think it'll take us to create the perfect clock?
Okay.
The one who will tell the exact time.
And I think the answer to that is we will never make a perfect clock. There's always going to be something that is going to mess it up a little bit. For example, just the fact that that clock is moving compared to me. Now you say, well, let's have it not move. How are you going to do that? if I have the clock on a table and I have a detector that's looking at the clock on the table, if the temperature of the table changes by the slightest amount, then the table will stretch, and that means the clock is moving compared to me, and there will be a Doppler shift. Now you say, okay, let's control the temperature. Fine, I can control the temperature in my lab to 1,000th of a degree, but I can't control it to 1,000,000th of a degree. Now maybe sometime in the future, I'll be able to control the temperature to 1,000,000th of a degree, but it'll still not be perfect. So nothing is ever perfect. And so the question is, how long will it take us to get to a part in 10 to the 21? And I'm guessing maybe another 5 years at the rate that things are going. That's not bad. A part in 10 to the 24, I'll probably be dead then. But, you know, the people who are still around, it's going to be really fantastic.
I wanted to ask a question. Can I? Hi, my name is Juzeliūnas, and today it's a pleasure meeting you. Today we're talking about Einstein, time, and the coolest stuff in the universe. I wanted to ask you, what was the coolest moment in your life besides being a winner of Nobel Prize?
Well, and besides marrying my wife, you mean?
Of course.
Or perhaps meeting her for the first time? Probably discovering any number of the things that we weren't expecting. That the temperature was too low, that we were trapping atoms in optical lattices. I would say it's hard to distinguish one of those amazing moments from another when we learned something that we weren't expecting. Those are the cool times. So let's come back to here.
Yeah. Yes. So I still have a bit of questions. This one's, I think, pretty awesome. I just need to correct myself. So if we manage to gather a large amount of the coldest stuff in the universe, let's say, and we put a person in it, wouldn't the person just explode? Because,
okay.
well,
So
or just
first
freeze
of
to death
all,
in a very little amount
First of all,
time.
let me give you an idea of how hard it would be to have enough stuff to put a person in. If you took all of the experiments done in the entire world since the beginning of laser cooling until now, and asked how much stuff has ever been laser cooled, and put it all together, it wouldn't amount to a grain of sand. That's how little stuff we have. Because when we make these gases I showed you pictures of with 100 million atoms, 100 million atoms does not amount to much stuff. And so it's almost impossible to have the kind of situation that you're talking about. But if you could, it wouldn't be that much different from putting somebody in liquid nitrogen. And people, I think they're probably a little crazy, but some people have arranged to have their bodies frozen in liquid nitrogen when they die, in the hopes that sometime in the future somebody will figure out how to fix them. And the idea is that the liquid nitrogen preserves them, because the kind of chemical and biological processes that cause decay of a human body are essentially stopped when you go to the temperature of liquid nitrogen. Now you might say this is totally fanciful, but in fact it's not entirely fanciful. It's absolutely routine in the dairy industry to freeze the semen of really good bulls that produce cows that produce a lot of milk. And so long after the bull is dead, you can make cows that will produce a lot of milk because you're using the genetic material of a really good bull. And the way they do it is freezing it with liquid nitrogen. So it's not entirely fanciful that you can preserve something about life using liquid nitrogen. But it has to be done extremely carefully. You have to do it because when you freeze tissues, normally what happens is you create ice crystals that puncture the cell walls, and you don't want that to happen. So it has to be done in a very careful way, and people have figured out how to do that.
On that side.
Yes?
All right. Good evening, sir. It's a great pleasure meeting you. I've got several questions as well, if that's all right. First of all, I would like to ask, since you've emphasized a couple of times that liquid nitrogen would be the coolest thing that we would encounter, I assume you have been in a few physics labs yourself. What is the coldest thing that you have encountered?
Right. Well, I mean, besides the things in our own laboratory, if I go to a low temperature physics laboratory, it's absolutely routine to have liquid helium, which is at a temperature of about 4 degrees. Now, if you take the liquid helium and pump on it, you can get down to a temperature below 2 degrees where it becomes superfluid and starts to do amazing things like crawl up the walls of a container. And by pumping on it, you can get down to maybe a little bit above 1 degree. And then if you use helium-3, then you can get down to 0.3 degrees. So that would be the coldest thing that you might think of as being a material thing. But I'm forgetting about dilution refrigerators. So there are these other kinds of refrigerators that use helium-3 and helium-4 in a really clever way to get down to 10 millikelvin. Okay? And I've certainly been in laboratories where they're cooling things down to 10 millikelvin. Now, to us, 10 millikelvin sounds like it's really, really hot. But for a low temperature physics lab, that's a pretty nice temperature, 10 millikelvin. And then there are other tricks that people can use called adiabatic demagnetization. I'm sorry just to throw out these terms, but just to give you some idea of where this all goes. And people get down to a few microkelvins of actual materials with this adiabatic demagnetization. So, so real things can get down to temperatures that are pretty cold, but they still don't get anywhere near as cold as what we do with laser cooling.
All right, thank you. And the second question would be in regards to the clocks and their accuracy. As we know, the Earth rotation is starting to speed up, and now we have what is called a leap second. So I was wondering, how do the atomic clocks adjust to leap seconds? Or
Yeah.
just explain about that.
Right. So what you do is the International Bureau of Time keeps track of this for the whole world. So everybody sends information to them about what their atomic clocks are doing, and they compile all the information to produce the best time for the whole world. And there's a whole bunch of different time scales. So let's talk about one of them that's based on atomic time. It's called TA1, temps atomique numéro 1. So TA1 is just the atomic clocks. Now, the trouble with that is that if you just stuck with atomic time, then little by little, you would find that at noon, at Greenwich, that the sun would not be at its highest point. And if you went some thousands of years, you might find that that noon was significantly different from what everybody thinks about it. And a lot of people think that's not a good idea. So instead, we have another time scale called UTC, for Universal Coordinated Time. And what that does is it slips these leap seconds in whenever needed to keep the Earth rotation synced with the standard time, which is UTC. So UTC is just atomic time offset by an integral number of seconds in order to keep sync with the Earth. Now, the Earth is slowing down on average. Every time, once in a while, it speeds up because of, say, an earthquake or something like that. And it's not a big deal for most people. We get a leap second every few years. Most people don't care, but some people do. And right now, there are tremendous discussions happening in the international community about whether we should continue with leap seconds or just let it go and not worry about the fact that we're 15 seconds off sometime in the future. We'll all be dead by the time, well, maybe not you, but I'll be dead by the time we're 15 seconds off. So it's a discussion that people are having, whether we should continue with the leap seconds or just make UTC the same as TA1.
Yes, hello. So if I remember my physics 101 correctly, the absolute zero is considered to be unreachable temperature. So in your field of lowering temperatures, are you doing it for the sake of discovery, or is there some holy grail you are working towards?
Well, maybe a little bit of both. It's always nice to have bragging rights to say that you've gotten the lowest temperature. But the real reason we do it is we want to do new kinds of experiments. We want to be able to do things to simulate materials, to simulate theoretical models better by having the temperature lower. The question of whether it's ever possible to get to absolute zero is a subtle question. Because temperature, to be completely strict about it, only makes sense in what we call the thermodynamic limit. That's a limit in which you have lots and lots of stuff. And we never have lots and lots of stuff, okay? We have, let's say that I had 100 atoms. I could, from time to time, get every one of those atoms into its lowest quantum state, and then you might say that's absolute zero. But not really, because if I did that same experiment 100 times, I might only get those atoms into the lowest state 50% of the time. So that's not absolute zero, because in the thermodynamic limit, that, it would depend on the details what the temperature would be, but it wouldn't be zero. I'd have to average it over all those different trials, and it wouldn't be zero. So I think it's still true that we can't get to absolute zero, but in some cases, for all practical purposes, it is absolute zero. And, that's wonderful. So we can do certain things that require zero temperature or near zero temperature, and it really works. But it doesn't work for all experiments, and then we have to work harder and get the temperature even lower.
I have a question.
Where am I looking?
Okay. The small one.
Ah, right, yes.
I'd like to know what temperature is the liquid state of oxygen in kelvins.
Right. So I don't remember exactly, but it's a little bit warmer than liquid nitrogen. So I think that liquid oxygen is somewhere in the 80s for the temperature at ordinary atmospheric pressure. So here's something that's really cool. Let's say that I've got a bucket of liquid nitrogen, like I have here. And let's say I put a test tube inside that bucket. After a few minutes, that test tube will have liquid oxygen in it because it condenses oxygen right out of the air. And with liquid oxygen, you can do some really cool things with fire. Because pure oxygen really allows fire, so it'd do just the opposite of what was going on with the match. If I had a bucket of liquid oxygen and I lowered the match into there, it would flame up really quickly. Again, the sort of thing you only do when you've had the right safety training. But liquid oxygen is warmer than liquid nitrogen by a little bit, and that allows you to make liquid oxygen from liquid nitrogen. In fact, sometimes when we're transferring liquid nitrogen in metal tubes, so we got a big bucket of liquid nitrogen, and we want to transfer it to someplace else, we send it through a tube, liquid oxygen will drip off of the tube. So it's kind of cool.
Hi. So this side really has a question now. Sorry, guys.
Wave your hand. Yes.
Yeah. So once my father said that every single science discovery is personally made for Warcraft. So as we saw the bottle filled with liquid nitrogen just blow up so quickly and so badly, would this coolest stuff and coolest atoms ever make a bomb that could blow out a galaxy or something? Because it seems like it could be so strong.
No. No. And in fact, the amount of energy involved in that explosion that you saw, it was pretty surprising, of course, but compared to actual explosives, it's really very small, a very small amount of energy. But at the same time, what you say is not so far from the truth. The first people to give me funding to do this work were the Navy. Now, why did the Navy give me money to do this? Because if they have better clocks, they know where their ships are. And if they know where their ships are and they know where their targets are, then they can do a better job of hitting their targets. So, you know, in a certain sense, this whole field got started, and I wasn't the first one to get money from the Navy to do this, got started because the Navy was interested in having better clocks. But one of the great things about the Navy over time is that they didn't care that much about whether it worked or how long it was going to take. If it looked like a good idea, they were willing to give you money for it. And it took us, I started to get money from them in about 1980, and we started to make good clocks in about maybe 90 to 2000. And so it took a long time before it got to there, and by that time we were doing all kinds of other stuff with these cold atoms that had nothing to do with the interests that the Navy had. So, so you know, it's a little bit of this and a little bit of that. You've got the, go ahead.
Yes, I have pretty simple question. Have you always wanted to be a scientist, and how you became one?
Yeah, so I have been interested in science since about as early as I can remember. Now, but of course when you're 5 years old, you're interested in everything, right? And so I can remember that when I was 5 years old, I'm not sure whether I had a clear understanding that you could be a scientist. I was interested in science, and I was doing all kinds of stuff that was related to science, but I also remember wanting to be a firefighter and to be a prize fighter and to be a cowboy. And I mean, that's what 5-year-olds think about. But probably by the time I was 10 years old, I was convinced that I wanted to be a scientist, even though I really didn't have any idea what it meant to be a scientist. And as I got older, it just became more and more clear to me that being a scientist was about as cool a thing as you could imagine doing. One of my mottos is that a good day is a day when you learn something new. And when you're a scientist, it's almost all good days because you're constantly learning something new. And sometimes it's something that nobody else knew. I can also remember when I was in elementary school that one of our teachers described to us what it was like to go on to higher education. You know, to go on to get an undergraduate degree and then to go and get a graduate degree and get a PhD. And I remember that it was explained that when you did a PhD that you had to write up a thesis, and that thesis would contain something that no one else had ever done before. And I thought, how could that possibly be? How could you ever do something that was new, that no one else had ever done before? And now we do that every day. It's just an amazing thing to do. I just can't imagine anything that's more fun.
So you showed a lot of cool stuff here. And of course, I mean, scientists, they have many more toys, you know, very expensive toys. I mean, we build the rockets, you know, we go to the moon, we have a shuttle which has 2.5 million parts. If you go to CERN, I don't know how many million parts are there, but you take a virus, you know, which is 15 different parts, or, you know, HIV, or the one which you actually felt miserable, you know, it has 30 parts. Don't you feel embarrassed that we are going to these places and we cannot work out these very simple things? That's the first question.
Well, sure. There's no question that we're not as efficient as nature. Evolution is an incredibly efficient process. On the other hand, it does take millions of years. So we could comfort ourselves with the fact that even though nature may be more clever than we are, that it has taken nature quite a long time to get to where it is. Now, it can make little adjustments pretty quickly, as we've seen with COVID, but so can we. So sure, I think we should all be in awe of what nature does compared to what we can do, but I don't think of it as trying to compete with nature. What I think of it is trying to understand what nature is all about.
In the title you put...
Yeah.
Have you ever done an experiment that didn't turn out to be fun?
Oh, that didn't turn out to be fun. Well, let's put it this way. I've done experiments that had parts that didn't turn out to be fun, but where ultimately the experiments themselves were fun. So let me give you an example. In the early days of laser cooling, we were trying to slow down an atomic beam, and one of the things we had to do was to make a magnet by winding wire around a tube. And the trouble was that the magnet was getting hot, and so we were trying to figure out ways of cooling it down. And every time we figured out a new way of cooling it down, it only worked for a little while until the magnet shorted out, and we had to make a new magnet, which took many days, and then try a new way of cooling it down. And then it worked a little bit longer, and then it failed. And finally, we got it to work, and then we did and learned some new stuff, and that was really cool. But it was a bit painful along the way. So I think that, but that's true of almost everything that's worth doing. That if it was easy, somebody would have already done it. So it's almost always hard the first time that you do something new. But then, after we learned how to do it, it was easy. And then we could go on to something else that was hard. And then that would be painful for a little while. And then we'd learn how to do that. And then we'd get the excitement of the new things that we learned doing that. So, as with almost anything in life, there are ups and downs, and there's hard work, but at the end, if you stick to it, it's great. Yes?
Yes, I don't know, can you? Yeah, so hello, I have a question. So you, first of all, it's kind of a two-part question. So first of all, why did you turn onto physics, from the sciences? And when you started learning physics in university setting, did you already know that you wanted to work with atomic clocks, or was that something that led to you as you were doing your graduate studies?
Right. Okay. So let me answer the second question first, because it's easier. No, I had no idea what I wanted to do as a career scientist. I had this crazy idea that I wanted to do nuclear physics because I'd read these books about the beginning of nuclear physics in the beginning of the 20th century, and it all sounded so exciting. And I read the biography of Marie Curie, and I was just so taken by that. It was just, her story was just so exciting and romantic. I thought, I want to do that. But then when I started working, well, there were other things that were interesting, and I was offered a position as a graduate student in a lab where they were doing atomic physics, and I learned the kind of things that allowed me to go into all this business that I've been talking about here. So no, I didn't have it all plotted out. It just happened. Okay, so why physics? Well, there's a couple of reasons that I often give. But remember, we're talking about a long time ago. And so my memory of what things were like when I was a child may be not perfect. And the other thing is that these reasons that I'm giving are almost jokes. I have a very bad memory, and it's getting worse all the time. In biology and chemistry and geology and other sciences, at least at the time that I was a kid, you had to memorize a lot of stuff. You had to memorize the names of the phylum and the order and the genus and the species of all these organisms in biology. And in chemistry, you had to memorize what was more electronegative than something else, and what would happen when you reacted them together, and whether it would be exothermic or endothermic. And I just didn't have a very good memory. But in physics, all you had to do was remember a few key equations, F equals ma, and you could do almost everything else just by knowing a little bit of math. So for a person who doesn't have a good memory, then, this is pretty cool. Now, the other thing is that even though biology and chemistry are incredibly interesting, biology is a little bit icky, and chemistry is a little bit smelly, and physics is really clean. So those are some of the reasons that I would give. But as I said, they're sort of jokes. Okay.
What do physics mean to you? Is it fun and games?
Well, it's a combination of fun and games. I mean, why would you do something for your whole life if you weren't having fun? I mean, it's not like you make that much money. I mean, we make enough to get by, but it's not like any physicists that I know get rich. The economists, those are the people who get rich. So, I mean, I guess there are people who invent something that makes them a lot of money. But anyway, so the point is, yes, I mean, it's about having fun, but it's also about doing something useful. So why did I start doing laser cooling? Because I thought that laser cooling would make better atomic clocks. And I knew that we needed better atomic clocks. I haven't really talked about what we do with better atomic clocks, but we use better atomic clocks both for things like testing the most fundamental theories of the way the universe works, and for doing things like high-speed synchronous communications, quantum computing. We need effectively atomic clocks. So all these things that can produce useful results can come from atomic clocks. So it's a combination of it being a whole lot of fun and the fact that there's actually something useful going on. But you know, I don't think that you have to be focusing on the use of something. Take something like Einstein's theory of gravity. In 1915, when Einstein came up with the theory of gravity, it was reported in the newspapers that only 3 people in the world even understood what the theory was about. Now, the story is that Arthur Eddington, who was presumably one of the 3, a friend comes to Eddington and says, "See here, Eddington, it says in the newspaper that only 3 people in the world understand Einstein's theory." And Eddington says, "Well, I don't know about that." And the friend says, "Please, Eddington, don't be so modest." And Eddington says, No, I was wondering who the 3rd person might be." Today, if we did not understand Einstein's theory of relativity, satellite navigation wouldn't work. So here is something that didn't have any clear application at all. And, you know, 100 years later, we couldn't do without it. So I think it's important to do things that simply satisfy your curiosity, because that's the way we make progress.
I have a question. Why do the properties of superconductivity increase while the temperature is lowered?
Okay, so if I've understood correctly, what you're asking about is what kinds of properties of matter change when the temperature gets lower. Is that the idea? I'm sorry, say it again?
The strength of superconductivity.
Oh, the strength of superconductivity. Okay, yeah. Okay, so of course, superconductivity is a very different field. It's done with materials, you know, what we call condensed matter. But we are using cold atoms to try to understand superconductivity better. So one of the things that you may have heard about is that in the last couple of decades, there have been superconductors that become superconducting at much higher temperatures than what the original superconductors did. The original superconductors, things like mercury and niobium, become superconducting at a few degrees above absolute zero. And now we have materials that become superconducting at 100 degrees above absolute zero. And there have been some recent reports of some you know, funny organic materials that under high pressure become superconducting near room temperature. So the trouble with those materials is that nobody really understands how they work. And what we're trying to do is to use cold atoms to elucidate some of the ideas behind what makes superconductors work. So it's not that we're trying to say get to colder temperatures so the superconductors will work better. We just don't have enough cooling power to cool down enough stuff that would make a difference. What we're trying to do is to understand how do these high temperature superconductors work? What is the physics behind them? Something that we very imperfectly understand now, and the idea is maybe if we understand it better, we'll be able to make those superconductors themselves work better. And at higher temperatures, that's what we really want to do. We want to make these things work at room temperature so that they can become more energy efficient machines for us, and we're not there yet.
Okay, so I think it's a time for a question. in today's meeting.
Have we
So
given all the prizes away?
almost, yes. So now we need to choose the last person.
Okay,
So
well, I'm
how
not going
many
to.
hands? Raise your
I'm
hand.
not. Okay, it's well. Let's see. You've already got a microphone, so I think it's you.
I have a question. If you have an atomic clock and it's the most accurate atomic clock you have made and in the world, how do you measure the accuracy of the clock if you don't have anything more accurate
Yes.
than that clock?
Right, very, very good question. Okay, so there's two ways that we address that question. One is you look at that clock and you think of all the things that could go wrong. And then you either estimate or measure how bad those things are. So for example, you say, what if there was a magnetic field? Then you put a magnetic field on deliberately and see how much it shifts the frequency of the clock, and then you say, I know that the field isn't any bigger than this, and so I can put a limit on how big that effect is. Or I change the temperature, and I see how much it changes the atomic clock, and then I think, okay, I can control the temperature this much. It's a big deal, the temperature. Or the density of the atoms, so they're colliding with each other, and those collisions affect the thing. And I ask, okay, how well do I know what the density of the atoms is, so I know how fast they're colliding? You put all those things in and add them all up in quadrature. That is, you take the squares and you add the squares together of these uncertainties, and then you take the square root of the sum. That's called adding things in quadrature, and then you say that's your uncertainty. And that's not bad, but the right way to do it is you build another one that's just as good, or you have somebody in another laboratory that's doing the same kind of stuff, and you somehow, it's not easy, make the two clocks communicate, and you see whether they're the same. So until you can do both kinds of things, people are skeptical about whether your uncertainty is really meaningful.
Okay, so you talked about various scientists that did such great research before they got their Nobel Prize. What about yours? What kind of research did you do before you got your Nobel Prize? Maybe some...
Well, the research that was recognized by the Nobel Prize was basically what I've been telling you about here.
Yes, exactly.
Before
what
that?
Things that led up to that, maybe?
Well, that's a good question. I started, you see, in a certain sense, it was a continuous evolution of my research in atomic physics. I began by, as a graduate student, by making precision measurements of magnetic moments of fundamental particles like electrons and protons. And that idea of precision measurement sort of informed my decision to go into atomic clocks, because it's another form of precision measurement. But I was also doing experiments looking at collisions of atoms that were excited by lasers. So that gave me the skills of using high precision lasers to excite atoms, which is another thing that you have to do in order to do laser cooling. So I guess it was a combination of a number of things that I did as a student that put me on the right path to doing these kinds of things. But the fact is that I spent a lot of time doing precision electrical measurements as well, which seems to have nothing to do with this. But I think that's really cool. And I gave a talk about that yesterday. And we've changed the definition of the kilogram because of the kinds of experiments that my colleagues and I did with electrical measurements. So it's all wonderful.
Listen, thank you so much.
So thank you very much. And actually, I asked the last question, but this is completely not completely true, because I will take advantage of being a chairman and would like to ask a question which probably the audience is interesting to hear. Can you comment about today's Nobel Prize?
Today's Nobel Prize. today's Nobel Prize, which I haven't even read what the citation is, but what I'm imagining it says is something like for experiments that showed violations of Bell's inequalities. Bell's inequalities were something that a physicist named John Bell, now sadly deceased, came up with in the 1960s, where he said, look, think about the most reasonable thing you might imagine. Let's say that what happens here is not going to affect what happens here in any time that is less than it takes a signal traveling at the speed of light to go from here to here. That sounds perfectly reasonable, right? And he derived some constraints on the way experiments would have to work if that were true. And it turns out it's not true. And that's what the guys who got the Nobel Prize this year showed, that they could violate Bell's inequalities. What Bell showed was that quantum mechanics, the theory that basically explains the way matter works, that theory violates this, what sounds like a perfectly reasonable principle. That doesn't work in quantum mechanics. And so what Bell did was he came up with, but no one had shown, you see, that it didn't work. So Bell came up with this very simple procedure about that suggested what kind of an experiment you can do, and the guys that got the prize did those experiments and showed that quantum mechanics is really, really weird. Because the idea that something that happens here could affect what happens here when they're far enough apart that no signal could go between them, that's pretty weird. And quantum mechanics is indeed that weird, and that's what they showed. Why is it important? Well, it's important to understand how the theory that basically describes everything that happens with materials and with atoms and whatever, that it's right. And it is. Everything, all the experiments have shown that it's right, but also it turns out that a lot of ideas of quantum information, which are becoming very popular these days, especially transmission of information in a secure way so that somebody can't eavesdrop on the information. Having quantum systems that are violating Bell's inequalities can guarantee the security of those systems. So it has very important current applications, and it was a really important step in understanding physics. Would you like to add anything to this? Because I think when I say something about the nature of local reality, I may not be saying it in the way a theorist would.
No, it's perfectly fine, thank you. So you are a very good theorist as well. So we would like to thank you, but before leaving, we would like to make a picture. So maybe first let us take a picture of the whole audience, but let us thank Professor Phillips for very nice.
How are you?
Here on the stairs,
okay.
And photograph the kids and you in the
So you have a wide-angle lens?
Yes.
Okay, so they tell me that I should go up a few steps, which at my age is non-trivial. And so is this good enough?
Yeah.
Oh, okay, we've got a professional doing this, so I don't have any problems with... Yeah, you must need a wide-angle lens. And I know you have one. See, I used to be an amateur photographer. So you don't have that wide angle lens. My guess is that it's not going to work.
But he did, or maybe I can do with my iPad.
Well, I think that the way to do it is you take a couple of pictures and then you have these programs that can stitch them together.
Mažena, gal galima tiesiog su iPhone nufotografuoti, ar čia nelabai?
Plataus kampo neišeis.
Neišeina?
We need white.
Palaukit.
And the people who don't want their picture taken are leaving.
Very different people, yeah.
Okay, now he's doing the stitching part. Okay, thank you. Thank you for your questions.
Oh, I forgot you can't write. Should I ask an off-science question for you?
Okay, why don't you come with me because I have to start dealing with some of the things that we have here. So I want to make sure that I don't lose any of the weights that I take off here.